Okay, in this video, I'm going to be going over how to just start these problems in chapter 5. I'm not going to go all the way through the problem, just give you a starting point. Gonna just go through them one by one, and if you don't need help on the one I'm talking about, just skip forward till you get to the next one. So let's see if I can get this to focus a little bit better. There we go, that's pretty good. Okay, so question 1. Only 2 horizontal forces act on a 3 kilogram body. So how do we do this? We're going to draw a free body diagram. There's our 3 kilogram body. One is acting due east, so we're going to go east at 9 newtons, and one is acting at 8 newtons, 62 degrees north of west. So there's west, so there's north of west, like that, 8 newtons, and there's 62 degrees. And then we are supposed to find the magnitude of the acceleration. So in a lot of these problems, it's going to be A is F net over m is kind of one starting point that we're going to be doing. We just need to figure out the net force. So other trick in these problems is you're often going to have something you're going to do in the x direction and in the y direction. Sometimes you'll keep them totally separate. In this problem, you'll bring them back together. So what do we need to do? We need to take this vector right here. We need to split it up into an x component and a y component. And it should be pretty quick for you to just go, if that's 8, then this side right here is going to be 8 cosine of 62. And then this sign over here is going to be 8 sine of 62. So then in the x direction, we're going to have this force in the x direction. And the y direction, we're just going to have this force. So you need to find the sum of these forces and then find the sum of this force, and then you're going to have to put them back together. So you'll get the sum of some forces. Eventually you'll get something in the x direction, something in the y direction. You'll have to re-put them back together to get your overall net force. And then with that net force, you're going to divide it by the mass to get the acceleration for that one. So it's kind of a lot to do for question 1, but there you go. Okay, let's see. Question 3. 1 kilogram body has an acceleration of 20 degrees to the positive direction of an x-axis. What are the x component and y component of the net force that's acting on it? So we draw a little free body diagram. We know it's going to be accelerating up in this direction. So here's the force that's acting on it. I'm not going to label it with this 2 because that's an acceleration. I can label this as 20 degrees. Oops. And I know that it's 1 kilogram, so maybe I can write that down as well. This time, I know that the net force is mass times acceleration. So I know the acceleration, I know the mass. I can figure out the net force. Once I figure out the net force, I just have to figure out the x component and the y component of like this. F net x, and, oh, sorry, this has been off the screen. F net y. Hopefully you're able to see what I'm doing there. So just to go over it again, because I was off the screen. F net equals ma. I know those numbers, find out the net force, and I can put them there and there. So that's question 3. And I'm going through some of these a little quickly because they're not that hard. Here's question 5 with this diagram that looks like this. 3 astronauts propelled by jetpacks, and we know the mass of this thing. We know what this force is. We know what this force is. We know what this force is. We know all their angles. Find the acceleration in unit vector notation. So once again, we're going to have A is F net over m, but we're going to have that in the x direction and the y direction. That's an A. So we're going to have to figure out what's going on in the x direction, what's going on in the y direction, and keep those things separate. So you're going to have to break down these forces into their components. So I'm going to have, where can I write this? I'm going to have my F1 right there and my theta 1, and then I'm going to have F1 in the x direction and F1 in the y direction. My F2 is already in the x direction. Then I'm going to have my F3. I'm going to have an F3 in the x direction and then F3 in the y direction. And then I just have to add them up. So I have to add up this y, and then this x, and this x, and keep them all separated. And then it's nice that it's saying you figure it out in unit vector notation. So you're going to get the overall net force, and then the acceleration is going to be the net force divided by the mass. So you can find the acceleration in unit vector notation, and once you have that, you can figure it out in the magnitude and the angle. Okay, moving right along. Here is question 9. I feel like there was one before 9. What happened to 7? Oh, here's question 7. There we go. Question 7 is about this diagram here. two forces acting on this block right here. Only one force is shown. Now I actually think that this is kind of a weird problem because ordinarily I wouldn't draw a force vector and an acceleration vector in the same diagram, but that's just what's going on here. So I would redraw this and draw a new free body diagram for it. So there's my object, there's F1, and there's another force somewhere, we don't know where it is, and that's what we're trying to find the second force. I think because the acceleration is going this way, I can assume that F2 is going to be going kind of down this way somewhere, F2, so that the net result of these is going to be something else. So how am I going to do that? Well, let's see. I can find, let me see, F, second force in unit vector notation. I know the acceleration, the overall acceleration. So I can find my net force. Sorry, what am I doing here? I can find my net force is going to be going in that direction like that. So I can also figure out what my value of my net force is going to be. F net equals ma. So I have my acceleration and I have this over here. So my net force is going to be 2 kilograms times 12 meters per second squared. So that's 24. So I know my net force has to be 24 and it has to be going in this direction. So I can now break down my net force into vectors as well. So let me redraw that a little bit here. So here's my net force, F net, and it's 30 degrees. So that's 30. So what I would do is I would call this one F net y and this one F net x. And then this is going to be F net cosine 30, and this is going to be F net sine 30. And yeah, I think you can go from there and kind of figure it out. To figure out what this F2 has to be, maybe I would break down F2 into F2x and F2y, and then you can kind of figure it out from there. So I don't want to do the whole problem for you. You got to do a little bit of work. Okay, so question 9. Let's see here. I feel like this focus is still not that well focused. Okay. Particle moves in xy plane according to this equation, and we want to find what is the magnitude and the angle of the net force on the particle. So the way we're going to attack that one is knowing that the v of t is x prime of t. So I can find the derivative of this one. Both of these, actually, because there's an x and a y. So that's vx of t. Vy of t is is y prime of t. And that's actually going to help me with the particle's direction. And then for the acceleration, I can get the acceleration in terms of time is going to be the time derivative of the velocity. And then the acceleration in the y direction as a function of time is the y derivative of the velocity there. So once I got acceleration, then I can figure out the force in each one. F net equals ma over here, F net equals ma over here, and then let's see, the magnitude and the angle. So once I get the two forces, I don't know what directions they're going to be going in, but I'll have an x component and I'll have a y component, and I can find the overall result. I don't know if this is the right quadrant or anything, but so you can work on that. Let's see, question 11. Particle moves along an x-axis being propelled by a variable force. So that's good. It's just a one-dimensional problem. Here's the position given by this. Great. So there's this kind of constant in there. At 3 seconds, the force on the particle has a magnitude of 36. So if I'm given the mass and the force, I can find the acceleration. So A is going to be F net over m. The net force is 36 and the mass is 2. I guess I should write newtons and kilograms. So that's going to give me 18 meters per second squared. Once I have that, then I can take the double derivative. I can get x double prime of t, find that out, and it should have something with a c in it, and then that's going to equal that. So I kind of did that whole problem for you, but anyway. Let's see, 13 is this one. There's 13. Shows an arrangement. 4 discs are suspended by cords. The longer top cord where are we? Top chord loops over a frictionless pulley, pulls with a force of magnitude 98 newtons on the wall. So that means we know that the tension here is 98 newtons, because it's 98 newtons over here as well, and the tension just kind of carries through, to which it is attached. The tension in the short chords are, we have T1, we have 2T, T3. What are the masses of the disks? Oh, okay, so this one's not so hard to do. If I know what T3 is, now theoretically I should draw a free body diagram for disk D down here. So let's do this kind of the more formal way. So there's disk D. I've got the force of gravity pulling down on it, and I've got T3 pulling up on it. Those have to be balanced. So my next step is I should write a net force equation. F net equals MA. I guess I'll pick down as positive. So this would be Fg minus T3 equals MA. Since it's stationary, that's 0. And now I know that T3 is going to be whatever the force of gravity is on this one. So did I have to go through all this to get there? Not necessarily. So I just know that those two things have to be balanced. This Fg right here is going to be, we're finding the mass. It's going to be the mass of D times G. So you can figure that out. Then for the next one, to figure out the mass of disk C, I think a nice way to do it is I'm just going to combine both of those together into one object. So there's my one object. I've got the force of gravity on it, which is going to be mc plus md times g. And then I've got this T2 acting up. That has to equal that, and you can figure that out. To figure out B, I'd kind of do the same thing. I'd group all these together as mass of, D plus mass of C plus mass of B. I put those all in one group and then do the same thing. So you can figure it out from there. Okay, 15. This is what we did in class. So I'm not going to really talk about it too much, but we talked about it in class a little bit. So that's fine. I mean, the basic idea is, in this situation, if this is 11 kilograms, then I can figure out that the force of gravity is going to be 11 times 9.8, whatever that turns out to be, and then that's going to be the reading on the scale in any of these situations. So there you go. Okay, 17. So now we're finally getting into some inclined plane problems. And if we haven't gone over this in class yet, then I will pretty soon to talk about how inclined planes go, but I'll just set up this problem. So we're looking for the tension in the chord and the normal force, and then find the acceleration. So to draw these free body diagrams, there's the block right there. Gravity is going to be going down right there. I'm going to label it on this side as Fg. I've got a normal force going up like this, Fn, and then I've got a tension going over there, which I'm going to write as T. And I'm trying to find the normal force, and I'm trying to find the tension. So what I need to do is I need to break down this gravity into components, one component coming this way, and one component coming this way. This is my same angle right here as it is right there. And then this component right there is going to be Fg cosine theta, and this component is going to be Fg sine theta. And then we just start to equate some things. I know in the up and down direction on the ramp right here that it's all balanced, so this is going to equal that. In this, I guess, I don't know, side to side direction for this one, and this is up and down direction, that's going to equal that. And then if the chord is cut, then I just have this as my force that's going to be accelerating the object down the ramp. So once again, I don't want to do the whole problem for you, but I just want to set it up a little bit. 25. This is a pretty easy problem here. This is just A is F over M, and then where that's the acceleration. How far will it go? X is 1/2 AT squared. How fast will it be going? V equals AT. Sorry, my lights went out in the room. I got to turn them back on. Okay, so I'm going to stop this video and then do the rest of the problems in a different video.